a few examples of solving equations involving exponents. This first one is where the variable is in the base, and so that's not actually going to be the most interesting and novel kind of thing that we're going to be focused on. But I figured I'd include one of these because the exponent is a fraction, and that can be a little confusing. So if 3 equals u to the 2/3, let me display that sucker. Then we just need to strip off that 2/3 power off the 3. We could rewrite that as 3 equals, there's a couple ways, the cube root of u squared. Okay, or you can always do it in the other order, and sometimes that's really useful. That's the cube root of u and then squared. Oops, lost it. Okay. But I want to actually going to stay with the fractional exponent, and I'm just going to say, what can I do to both sides here that will undo that? I'm going to take both sides to the 3/2 power, and that's the reciprocal of 2/3. Why is that useful? Well, rules of exponents, as always. U to the 2/3 to the 3/2, those exponents multiply, and that's nothing more than u. And we're done, right? Well, it depends on exactly how we want to write this. 3 to the 3/2 might be a fine way to write that, but we could also say, okay, that means that u, 3 to the 3/2, is going to be the square root of 3 cubed, or the square root of 27. Okay, or 3 root 3. That'd probably be a nice preferable answer. Or you could get it as a decimal as well. Okay, so the main thing is fractional exponents. Using rules of exponents is super helpful there. And then you still need to know what a fractional exponent is when you transfer it over and it's become the reciprocal. Okay, so what we're really focusing on right now in my class is things where the exponent is in the variable, or that's what's going to come up from our investigations. And we're going to need to be able to solve equations like this. And these two are fairly contrived so that we can do it without any additional technology besides thinking hard about rules of exponents. But it's a good start. So 3 to the 2x, the key here for these simple equations is that I claim I can write this expression as a power of 3. And if I can write both sides as some power of 3, then I'm going to be able to equate the powers. So let's see how that works. On the right-hand side, it's 3 to the 1/2, that's another way to write root 3, divided by 81, well, I'm going to say that's times 3 to the -4th. Or in other words, it's just 3 to the minus 7/2. I'm adding the 1/2 and a -8/2. I'm getting -7/2. And the key thing is that one thing about exponents is that there's no way to raise 3 to 2 different powers and get the same expression. So if the result is the same, the exponents must be the same. So I can just say that 2x must have been equal to -7/2. And therefore x equals -7. Okay, and so we can check that by saying, okay, 3 to the -7/2, oh yeah, okay, that's the left-hand side with x put in as -7, and indeed, I should get root 3 over 81. And you could even be paranoid and check both sides on a calculator or something if you want. Okay, so here, x equals -7 turns out to be the solution. Okay, another quick one, pretty similar, but maybe just slightly different. I've got 49 to the 3x, let me display that sucker, equals 7 to the 2x plus 10. Again, if you can, and there's no guarantee that you can in general, but if you can, try to express both sides using the same base. So the key here is that 49 is secretly 7 squared. Okay, so now I've got 7. They're both exponential expressions with base 7. Well, let me use rules of exponents. The 2 and the 3x multiply. And so I've got 7 to the 6x is 7 to the 2x plus 10. And again, the only way that those could end up being equal is if I'm raising 7 to the same power. It's a fundamental thing about exponential expressions. It's not trivial that that's true, but it is true. So the only way that could happen is the exponents are equal. And so 4x equals 10, x equals 10/4 or 5/2. Okay. And it can be interesting to see, well, what is the number on both sides of those? Well, okay, so 49 to the 15/2, does that equal 7 to the, well, 5/2 times 2 is 5 plus 10, 7 to the 15. Yeah, it does, and they're both pretty big numbers. Let me just go ahead and evaluate that. Ooh, they're both about 4 trillion. So these actually are going to be about, the only way they match up is they're both about 4 trillion. They're both 7 to the 15th, and that's going to happen when x equals 5 halves. So real quick, let me just contrast that with a problem. And put these question marks here because I'm not going to try and solve this yet. 10 to the x equals 372. That's a very, very reasonable problem. We'll see exactly where that comes up in real life. Some fixed base to a variable exponent is equal to some target number. What is this number going to be? Well, we actually are going to need a new technology to describe that process, and that's going to lead to logarithms. There's no nice number x that gives you 372. It's not a nice power of 10. It's certainly not an integer power of 10. It's not 1 or 10 or 100 or 1,000. And it's not even like 10 to the 3 halves or 5 halves or something like that. It's not even 10 to a rational number. And so I wanted to contrast that. If you think using this technique was going to solve all problems, it's not going to. They were pretty contrived. The 49 and the 7 had to relate in a nice way, have this kind of technique and have a really pretty answer. So this is going to be the future where we're going to look at logarithms.